Hello everybody, welcome back. Today we're going to take a look at a type of problem that you can solve using multiple integrals. Okay, so we have a rectangular lamina here that has these vertices and this specified density function. So we're supposed to find the total mass, x and y bar, which are the coordinates of the center of mass, ix and iy, which are the moments of inertia, and the moment of inertia through the center of mass about a axis parallel to the z-axis. Okay, so let's get started here. I have a sketch of our lamina here. The lamina, it just means that it's thin enough that we don't have to worry about the thickness at all. And we have these lines here are constant density lines, approximately. So anywhere along this line, for example, the density is 1. Along this line, the density is 2, 3, 4, etc. So you can see that as we're going in this direction, we're increasing a lot in our density. So, yes, our density. Um, our density function, we usually say density is rho, uh, the Greek letter. And so this is our density function. And so what we would normally do if we had constant density would we would take our area times our density, and that would give us our total mass, which is what we're trying to find with m. However, in this situation, since we don't have a constant density, how are we going to do that? Um, so we're going to divide it up into little patches of mass. Well, patches is not necessarily the correct term for that, but it'll work. Um, so what is the what's the actual mass of each little patch? Well, the answer to that is it's the density at that point times a little piece of area. It would be a little piece of volume if we had to deal with thickness, but we don't. So the density evaluated at that point times this little patch of area is this little patch of mass. And in this coordinate system, um, our density is xy, and our little patch of area, if we were just to draw one in here, little tiny patch of area, it's a little change in x times a little change in y. So we can rewrite that as just dx dy. So this is what each little patch of mass is. So substituting that in here, since we have two differentials, we have to have um, two integrals, but we'll put the limits of integration too. Our y varies from 0 to 2, 0 to 2, and our x varies from 0 to 3. And with these limits of integration, we're making sure that we're taking all of the total x amount and the total y amount um, in order to get our total mass and other properties of the entire shape. Okay, so this we can do this integration. So this is 0 to 2, um, and then our x turns into a x squared over 2 from 0 to 3. And don't forget our y here, dy. Okay, so um, from 0 to 3, so 3 squared is 9, 9 halves. Since that's a constant, we can take it out of the integral. 9 halves, 0 to 2 of y dy. And that is equal to 9 halves times y squared over 2 from 0 to 2, which is equal to 2, which is equal to 9 overall. So our total mass of this whole thing is equal to 9. And okay, to find our x bar, the x bar is the x coordinate of the center of mass, or the center of gravity, whichever term you prefer. And that it's equivalent to like an average, a mass weighted average of the entire thing. So it's a constant. So we'll write the sum of the mass, or the total mass with our x bar is equal to x dm. And since this is a constant, we can write it out in front. So that would be x bar dm equals x dm. But we already know what this here is because we just calculated that. That's just our total mass. So 9 times x bar equals, and we can substitute in what we know already from up here, 0 to 2, 0 to 3, and don't forget the x in there. So this is a x squared y dx dy. Okay, so this is equal to 0 to 2, y cubed over 3, 0 to 3, y dy. Okay, so this is equal to, when we plug this in, our 0 is nothing. Our 3 is 3 cubed over 3, so that's 9. 9, 0 to 2, y dy equals 18. Okay, so typically, oh yeah, wait, hold on. So this is equal to 9 x bar. So our actual x bar, once we divide that out, is equal to 8, not 18, is equal to 2. So that means that, so from here, 1, 2, 3, 5, okay. So 1, 2, 3, 4. This is 1, 1, 2, 3, 4. This is 2. So our x bar is actually along this line, up and down. Okay, so now we need to find our y bar. Y bar, well, yeah, we'll write it the same way as we did the other one. Y bar, that equals that. Which means that 9y bar is equal to 0 to 2, 0 to 3, xy squared dx dy. Okay, so doing the first integration like we did before, this gives us x squared over 2 from 0 to 3, y squared dy. Okay, so once again, this is 9 halves, 0 to 2, y bar, or not y bar, y squared dy. Okay, so this is 9 halves, y cubed over 3 from 0 to 2. So that's 8 over 3. Okay, so this is 9 halves, 8 over 3, which is equal to, let's see, cross multiply there, that's a 4. And yeah, so this that's a 4, and then that's a 3. Yeah, so that's 4 times 3, which is equal to 12. And then finally, dividing out that 9 again, our y bar is equal to 12 over 9 equals 4 over 3. Okay, so calculating that out here, 1, 2, 3, 4. Okay, 4/3, let's see, 4/3 would be about here-ish. So that means that our center of mass is actually about here, more or less. And that makes sense because it's a lot heavier, it's a lot more dense over here than it is over here. Which, remember, that was just our practice patch of area. So it makes sense that it would be about here. It's reasonable. So yeah, our center of gravity, our CG, is at 2/4. Doesn't ask for that, but it it's good to know that anyway. Okay. Um, then what is our x, or our moment of inertia around x? So, in order to do this, um, we take the integral y squared dm. Um, so substituting in what we already know, that's 0 to 2, 0 to 3, x, and this is y cubed this time, dx dy. And as usual, that's a 9/2. We've seen this integral before. Y cubed dy. And so this is equal to 9/2 y to the 4th over 4 from 0 to 2. So it would be 16 over 4 is 4. Okay, so this would be 18. It would just be 18. Okay. But normally we write moments of inertia and such in terms of m. It kind of makes sense to do that. So we're going to say that this is equal to 2m. And for our IY, we do the same sort of thing, but this time with x squared dm. Okay, so we write this all again. This time it's a x cubed y dx dy. Okay, so this gives us a 0 to 2, x to the 4th over 4 from 0 to 3 y dy. So this is going to be a constant, and the constant it's going to be 81 over 4. And we'll just keep that out in front since it doesn't affect anything. 0 to 2 y dy. As usual, it's that's 2. We've done that integral plenty times also. So this is 81/2. Okay, so what exactly is the multiple of this? We divide it by 9, so that gives us dividing it by 9 gives us 9/2 m. Yep. So, and then we finally get to use these formulas here that I've had here sitting from the beginning. So we want Im around an axis parallel to the z-axis. It's easiest to do that when you actually have the moment of inertia around the z-axis. So Iz, for this type of lamina problem, Iz is equal to Ix plus Iy. So this means that we have Iz is equal to 13 halves m, because you add 4, yeah, all that. So, and then we get to use this other formula here. So this is the parallel axis theorem. This is the moment of inertia around a parallel axis to the axis of center of mass, axis through the center of mass, and then d is the distance between the two axes. So flipping this around, Im is equal to Iz, because we're talking about a parallel axis here, minus m, which is the mass, d squared. And the d squared is actually, so that the z-axis is here at 0. So the d squared is actually the distance between, the distance between it and the center of mass squared. So our d is going to be equal to, actually, Yeah, well, yeah. So our d is going to be equal to the square root of, let's see what, yeah, right here. 2 squared plus 4/3 squared equals square root of 4 plus 16 ninths. And then d squared obviously is the square of that. So this gives us im is equal to 13 halves minus 13 halves m minus m 4 plus 16 or 16 ninths. Okay, so here, hold on, let me just calculate this. Okay, so yeah, so this is equal to m times 107. Well, okay, yeah. So just first before we do that, minus 52 ninths. Then in order to get common denominators, we multiply by the bottom of the other fraction, and we get 117 eighteenths minus 104 eighteenths equals to 13 eighteenths m, and this is our final answer here. These types of problems are pretty common in engineering and physics. In fact, you learn how to do these problems, you kind of learn some cheats on how to do them as early as like your second semester of engineering school in a class called statics. At that point, you haven't learned about multiple integrals, so they teach you some tricks on how to not do them. But then once you learn about them, it may not look easier, but it is easier to do them this way. It has more physical significance, and yeah, you do these problems all throughout your engineering school, including your junior and senior classes. So might as well learn how to do them now. Thank you everybody for watching.